So welcome you to this tutorial session. So if any one of you have any doubts, you may ask the doubts from anywhere.
So from assignment 4.
Assignment 4, yes. What is the problem?
Sorry, sir, from assignment 5, question number 3. I have a doubt.
Question number 3. Okay, yeah.
Sir, there is a expression like dd alpha of gamma alpha is equals to gamma dash alpha by gamma alpha.
Right.
How is it coming?
So you see, let me just use the whiteboard. So, so you know that gamma alpha function is defined as 0 to infinity, e to power minus t to power alpha minus 1 dt, right? That is how the gamma alpha function is defined for any alpha greater than 0. Is that okay?
Yes, sir.
So I take the derivative of this, d by d alpha with respect to alpha of gamma alpha. That becomes d by d alpha of 0 to infinity, e to power minus t to power alpha minus 1 dt. All right. Now the issue is about taking this derivative inside. Now one can justify using dominated convergence theorem that e to power minus t to power alpha minus 1, because it is an exponential function and it is just a polynomial kind of a thing. So this quantity would always be less than or equal to some e to power minus d times t. So it is integrable, right? So by dominated convergence theorem, I can take the derivative inside, right? D by df, because of this exponential being over here, and here only polynomials, so I can still bound it by something which is integrable. So d by d alpha of e to power minus t to power alpha minus 1. So this I do by dominated convergence theorem, right? Which you call as a DCT. Changing of what is it by dominated theorem says? If mod of fnx, so if mod of fnx is less than or equal to m, or is less than or equal to g, and integral g is finite, then you can change the limit and integral sign. That is what it says. That is what. So that is what is happening over here. I have to take a limit with respect to alpha. So I bound it by something which does not depend on alpha. Because it is a polynomial, so I can bound it by something bigger, so that it is bounded by that quantity. And then that quantity is integrable. So I can take the derivative inside. Is that clear?
Yes, sir.
What is this quantity? Because actually this e to power minus t to power alpha minus 1, if you have to look at modulus, it is only way positive. You can write down this as e to power minus t by 2 into e to power minus t by 2 to power alpha minus 1. Right? Now this is exponential still, although I've taken a power half. And this is t. So I can always make this quantity less than or equal to something. Right? Because you see e to power t by 2, for example, any for e to power t by 2 would always be greater than or equal to t to power m by 2 to power m by factorial m, right? Because e to power t has expansion 1 plus t square by 2 plus t cube by factorial 3 and so on. So if I take a particular term, mth term, it will be this, and since t is positive, so this would always be greater than this for every t. So e to power minus t by 2 would always be less than or equal to t to power something. Right? So I can suitably choose m so that it is, everything is nice. So, okay, so now I take the derivative with respect to alpha. What is the derivative with respect to alpha of t to power alpha minus 1? Log t. Right? Log t into t to power alpha minus 1. Because what is the derivative of d by dt of a to power t? It is log a into a to power t. And that is what I have done over here. So if I define, so this is gamma prime alpha. So if I define gamma prime alpha by gamma alpha, it becomes 1 upon gamma alpha, 0 to infinity, log t e to the power minus t to the power alpha minus 1 dt, which becomes 0 to infinity log t, and then this is a density of a gamma e to the power minus t to the power alpha minus 1 gamma alpha dt. This is a density of gamma 1 alpha. So this becomes expected value of that random variable, expected value of log of that random variable. Does that clarify your thing or?
No, sir. I can do this thing. That is expectation of log x equals to this, but
Right. So this expected log x is psi alpha, right? This is what you have defined as a psi alpha.
yes, sir.
So what is your doubt? So psi alpha is same as expected log of x, where x is a gamma 1 alpha random variable. That is what I have written down.
But,
Oh,
sir,
sorry. Oh,
yeah.
you are. Oh, sorry. This should be log is missing over there. D by d alpha of gamma alpha. There should be a log over there.
Okay, okay, huh.
Right, right. Because you see, gamma prime alpha upon gamma alpha I have written down correctly, but log is missing over there. So psi alpha is actually d by d alpha of log of gamma alpha. Right? Because then also only this is psi prime alpha by psi. Okay? Sorry, gamma prime alpha by gamma. So gamma prime alpha, psi alpha is same as gamma prime alpha upon gamma alpha, which is d by d alpha of log of gamma alpha. Does that, yeah, so there is a typo over there. Is that okay?
Yes, sir.
You want me to do the other parts?
No, sir, it's fine.
Fine, okay. Yes, any other doubt anybody has?
So for the part 2 of problem number 8 from this assignment.
Part 2 of problem number 8, yeah. AMGM inequality.
Yes, sir. The
Right.
first one is fine for me, but how to prove that? HMGM.
HMGM? Okay, so just note that if you try to, you can get an idea if you just see. Yeah. So you see, if you take the log in the second inequality, it says summation wi log ai is greater than or equal to minus log w log of summation w by ai, right? Is that okay? That is what second means. So let us look at a random variable x, which takes value 1 upon a1 with probability w1, 1 upon a2 with probability w2, and let us say 1 upon an with probability wn. This is a proper distribution because summation wi is 1, right? So this is a proper random variable. Now let us look at hx equal to log x function. What kind of a function this is? Concave, right? So I consider minus 1 log of minus 1 minus log x. It is a convex function.
Yes, sir.
So what do you get? Expected value of h of x would be greater than or equal to h of expected value of x because it is convex. Expected value of h of x means expected value of minus log of x, right? Will always be greater than or equal to log of expected value of x. Is that okay?
Sir, is it minus, I think.
Minus log of x, right? Or in other words, log of expected value of x would always be greater than or equal to expected value of log of x. Is that okay?
Yes, sir.
Now let us look at what is expected value of x over there. Expected value of x is nothing but summation wi by ai, right? Summation 1 upon ai w1, 1 upon a2 w2, and so on. So this is this. What is expected value of log of x? It is summation I is equal to 1 to n log of 1 upon ai into wi. and log of 1 upon AI is same as minus log AI. So it becomes minus summation I is equal to 1 to n log of AI into WI. This can be written as minus summation I is equal to 1 to n. WI log AI can be written as log of AI to power WI. Right? Now this is a sum of logs, so that can be written as minus log of product I is equal to 1 to n AI to power WI. Is that okay? So now I just put it over here. So what do you get? Log of expected value of x. What do you get? Log of expected value, yeah, log of x. Log of summation WIAI. Right? Log of is greater than or equal to expected value of log of x, which is minus log summation I is equal to 1 to n AI to power WI, which can be written as log of product I is equal to 1 to n. Right? So that's just that follows, right? That is what you have to prove. Right? Is that okay?
Okay, sir.
Because this you can take all on that side and then because minus. So this is same as log of product I is equal to 1 to n AI WI would always be greater than or equal to minus log, but minus log can be written as log of 1 upon summation WI by AI. And log is an increasing function, so you know that if log of x is greater than or equal to log of y, that means x is greater than or equal to y. So that means product I is equal to 1 to n AI power WI would be greater than or equal to 1 upon summation WI. Is that okay?
Yes, sir. Perfect.
Yeah. Any other doubt anybody has?
Sir, one last doubt from the problem number 9.
Right.
How to proceed with the part 1? I mean,
Okay.
how to proceed with this kind of problems?
So before that, let us try to see what is a randomized estimator. Randomized estimator is always a random variable which has a distribution, right? So after you have observed, it does one more randomization, right? I gave you an example that say, look, a non-randomized estimator is after you have taken the observation, you immediately tell what your estimator is. So for example, X bar. After data has been collected, it says sum all the observations divided by n and you take that as an estimator, right? What happens in the randomized estimator is it says, look, after you have taken an observation, don't take the decision. You perform another experiment based on what you have observed, and whatever is the random outcome of that experiment, additional experiment which you are performing, you take that as an outcome. So for example could be, okay, a randomized estimator could be you observe X bar. Suppose you have observed X bar, then it says now you generate one observation from computer from normal
X bar comma 1.
you have observed and 1. And then whatever is the outcome, you take that as an estimator. That is a randomized estimator. So what is happening over here is, here, for example, this randomized estimator is given to be x1 plus x2 by 2. So what is given to you? x1, x2, xn, IID, or it is a random sample from normal theta. My estimator is this. This is distributed as, right? This is randomized by, why? Sorry, not this. Normal x1 plus x2 by 2. So what it says is, it says you observe x1, x2, xn. After you have observed x1, x2, xn, discard x3 to xn. Just take the mean of x1 plus x2, x1 and x2. Whatever mean comes, then you generate one observation from a normal distribution with mean as x1 plus x2 by 2 and variance as 1, and you take that as an estimator. That is what your randomized estimator is. Right. Now, if you recall, we had done a result which says if t is sufficient, and suppose this has a distribution px, right? Because it depends on what you have observed. It is a probability distribution pxa. For example, pxa you know is how much? It says Px means what action you are taking. Your action is you are generating one observation from normal x1 plus x2 by 2. So its PDF is 1 upon root 2 pi e to power minus half a minus x1 plus x2 by 2 whole square. Is that clear? Because that is the density of Px.
Yes, sir.
Okay. Now, if you recall that result which we had said that, look, if you are given a randomized estimator, I can always find another randomized estimator based on a sufficient statistic whose distribution is, whose risk is same as the given randomized estimator. So if T is sufficient, I find a new estimator, delta T, let me call this as delta star T. This has a PDF, let me call this as a P star XA. And how this PXR is given? It says you take this expectation of this minus infinity to infinity PXA with respect to conditional distribution of X given T. X. So integrate whatever is the original estimator's PDF is with respect to the PDF of X given T. Here X has to be integrated out. So that means this everything would depend finally on T. So you'll get an estimator based on T. So basically this estimator where T is a sufficient statistic has the same risk as delta X that we proved in the class. Is that clear up to this point?
Yes, sir.
Okay. So now I know my PX, I know PXA. I need to find out what is the expectation of that with respect to conditional distribution of X given T. So what I do is my delta star T in this case would be minus infinity to infinity. PXA is this quantity, 1 by root 2 pi e to power minus half a minus x1 plus x2 by 2 whole square, and then P of X given T, X given T. So what is this? You are taking it. So this is a density and this is a function. So you are taking an expectation also of this with respect to conditional distribution of X given T. This was anyway X. So what you do is this is same as expected value of 1 by root 2 pi e to power minus half. A remains as it is because it's only expectation is taken with respect to conditional distribution of x1, x2 given T. X1 plus x2 by 2 whole square. Given T is equal to T, T is my X bar. So X bar is equal to T. Is that okay? Is that okay up to this point?
Yes, sir.
Okay. Now I try to use the Basou's theorem. So I try to use some ancillary over here. I know that x1 plus x2 minus x bar would be ancillary, right? Because x1 plus x2 would be x1 plus x2 by 2 minus x bar would be ancillary because x1 plus x2 by 2 would be normal with mean theta and something, and x bar also with mean theta. They are linear, so it would be 0. So that means what I do is I write down this as expected value of 1 by root 2 pi e to power minus half a minus x1 plus x2 by 2 minus x bar, right? Plus T, because x bar is same as T, so I have added and subtracted whole square given x bar is 1 T. Is that okay? Up to this point?
Yes, sir.
Now, this quantity is ancillary. No, this would be plus, right? Plus here and minus here, right? Because it is e to power minus x1 plus 2. This is ancillary.
So why?
Because x1, x2 are already normal theta 1, right? So this quantity becomes, if you look at minus of that quantity, so x1 plus x2 by 2 minus x bar, it is a linear combinations of normal. So it will be normal. What would be its mean? Theta plus theta by 2 theta, and x bar anyway has a theta, so 0. And variance anyway would be linear combination of variance, which anyway is known, right? Is that clear?
So, sir, that should be x1 plus x2 by 2 minus x bar.
Doesn't matter. Minus is there, so I take minus and then put everything inside the bracket. See this quantity, if you look at, this is 1 by root 2 pi. Doesn't matter, no? E to the power minus half a minus, I put everything now in bracket, x1 plus x2 by 2 minus x bar. That means plus t would come, plus x bar would come. I make it minus x bar, but x bar is fixed at t, so I make it that t and give an x bar. Is that okay or not?
Yes, sir.
This whole square. Right? Because what is this? Now this is ancillary. This is complete sufficient statistic. So this conditional expectation would be same as unconditional expectation. So this is same as 1 by root 2 pi. Expected value of e to the power minus half a minus t, right? A minus t minus x bar 1 plus x bar 2 by, sorry, x1 plus x2 minus 2 minus x bar whole square. Is that okay? Now let us look at x1 plus x2 by 2 minus x bar. What is its distribution? Yes? It is normal because I have to take this expected value. So I just, it is normal with mean as 0. What is the variance? Variance of x1 by 4, so 1 by 4. Variance of x2 by 1 by 4. Plus variance of x bar, which is sigma square by n, so 1 by n. Then minus 2 times covariance of x1 with this, so minus 1 by n. Same thing, covariance of x2 with x2 by n would come over 2 times, so 2 gets cancelled, minus 1 by n. And how much that becomes? Normal of 0. 1 by 4, 1 by 4 is half. Minus 1 by n, right? 1 by n gets cancelled, half minus 1 by n, so which is normal 0, n minus 2 by 2n. So what I do is I define z, which is root 2n upon n minus 2 times x1 plus x2 by 2 minus x bar. This would have a normal 0, 1, right? That I know. So I put that value over here. So this becomes 1 by root 2 pi. Expected value of e to the power minus half a minus t minus, what does this quantity becomes? x1 plus x2 minus x bar. x1 plus x2 by 2 minus x bar becomes root n minus 2 by 2n z whole square, right? Now you can calculate this. This is 1 by root 2 pi. Z is normal 0, 1, so it is e to the power minus half a minus t minus root n minus 1 by 2n z whole square into z is normal 0, 1, so 1 by root 2 pi e to the power minus z square by 2 dz. Now you can make this as a perfect square, right? Because there's a z square over here, z square over here. You can make it a perfect square, you can solve it, and then you can get the PDF. Is that okay?
Okay.
So you get a PDF which is again normal. So it is going to be a normal one that you know, right? With variance, in fact, if you want, you can do it 1 by root 2 pi. In fact, 1 by 2 pi it becomes root 2 pi. E to the power minus half becomes common. Then z square plus n minus 1 by 2 and z square. So 1, this is root of n minus 1n. So 1 plus n minus 1 by 2n. So that is 3n minus 1, right? 3n minus 1 z square. So 3n minus 1 by 2n z square. Then that becomes the factor of common z square. Then minus 2 root n upon n minus 1 z a minus t, right? And then e to the power minus half a minus t whole square, right? That you can, now you can make this as a perfect square, so that becomes z minus root n upon n minus 1 a minus t whole square, and then a minus t whole square. So it would be a normal with mean t only, which is x bar. So it will be some normal with mean x bar and variance, which will depend on n. Right? Is that okay? So your delta 1x, you want me to solve it, or you can do it now? You see, when you solve it, you'll get a density of the type 1 by root 2 pi. There will be some factor of Cn over here, e to the power minus Cn by 2, a minus t whole square. Right? You can simplify that. Cn you can determine, right? Because this, just look at this perfect square will come, and this integral will integrate out, because you know that minus infinity to infinity, e to the power minus x minus mu whole square by 2 sigma square is same as sigma root 2 pi. So once I'm making a perfect square, that will give me the value of this integral. So only the term of a minus t square will come outside, because that doesn't involve z. So it will be, so that is the reason I have written down this as a minus t whole square anyway would come. There would be a factor of Cn. So what is this? This is delta. So that estimator which improves upon this, what are you calling? So delta 1x is now normal with mean as t, which is x bar, and variance as 1 by Cn. Yeah, 1 by Cn. Is that okay?
Okay, sir.
So this is again randomized estimator. What it says is, this says that what you do is you calculate x bar. The earlier one was saying that you calculate only x1 plus x2 by 2. It is saying you calculate x bar, and then you do all this, right? Then generate one observation from normal x bar and 1 by Cn, and they take this like this. Now, if you have to consider the second one, if loss function is convex, even this can be improved by expected value of delta 1x. This expectation is with respect to this randomization which you have. And what is the expected value of this? This is x bar. So the second part, which says under the square error loss function, find a non-randomized estimator better than delta. Because if loss function is convex, then I have done a result that one doesn't have to consider randomized estimator. One just consider the mean of that randomized estimator, and that would be better than the given randomized estimator, provided your loss function is convex. Square error is a convex loss function. So I just take the mean of this random variable, which is x bar, and that would be better than delta 1x. I can call this as delta 2x. So I found a one non-randomized estimator, which is better than this randomized estimator. Does that make sense for you?
Yes, sir.
So you see, the first part says, if you have to find a estimator that doesn't require convexity, it only says given any convex function, given any randomized estimator, I can find a randomized estimator based on a sufficient statistic whose risk is same as that of a given randomized estimator. Now in normal theta 1, x bar was a sufficient statistic, in fact minimal sufficient. So I just take the expected value of a PDF of the estimator, which was x1 plus x2 by 2, with respect to conditional distribution of x given t. So that means I have to take a expected value of this quantity. That requires slightly tricky Basou's theorem, because I wanted to make it ancillary, because t is given to be x bar, and I know that x bar is complete sufficient. So if I can make here ancillary, my problem would be simplified to a large extent. And that is what I have tried to do over here. And then it's a simple algebra. Then the second part, we know that if your loss function is convex, then given any randomized estimator, I can get a non-randomized estimator, which is better than that. And what would be that non-randomized estimator? It says just estimate it by its mean. Whatever randomized estimator is there, take its mean. The corresponding non-randomized estimator would be better than this because its mean would only depend on x bar. There is no randomization. Mean is a fixed quantity. So it says take x bar. That would be better than this. Is that okay?
Okay, sir.
Okay. Any other question anybody has?
So,
Yeah.
so
Yeah. What's happening?
hello, sir.
Yeah, I'm hearing you. You're only calling sir, but not asking any question.
Oh, actually, sir, if the loss function is not convex, then
Only the second part you can do, right? First part, you can find an estimator. So if loss, so there are two results, right? First result is about non-convex loss function. That result we did. What it says is, given a randomized estimator, let's say delta x, which will have some density. Let me call it as px, or a distribution. We can find a randomized estimator let me call that randomized estimator as delta naught x, having PD of px star a, which has, for which the risk function of delta naught would be same as r theta delta for every theta. And how do you construct this delta naught? Delta naught, for delta naught, I just need the density. Px star a is basically, it says, take the density of the original estimator, which is not depending on sufficiency. Take its expectation with respect to conditional distribution of x given t, where t is sufficient. Okay. So then this delta naught and they will have a same risk function. The second thing is, for convex loss function, given any randomized estimator delta x, which has, let us say, some density px, yeah, we can find convex loss function in D, right? So L theta D and convex in D, not in the parameter. We can find a randomized let us say delta star. And what will be this delta star? It will be just mean of this delta x. Now, when I'm taking mean over delta x, the randomization is not over x, over the first, which is better than given randomized estimator, which was good. Right? So these are the two results. So when loss function is not convex, you cannot say anything except for the fact that if you are given a randomized estimator, I can find another randomized estimator based on a sufficient statistic whose risk is same as that of our original estimator. That is the best you can do in the case where loss function is not convex. But if your loss function is convex, then given any randomized estimator, you can find a non-randomized estimator, which is nothing but a mean of that randomized distribution, which is better than that. That means, what does that mean? The risk of delta star would always be less than or equal to risk of delta for that decision. So here it is not equality, it is always better if your loss function is convex. Is that clear?
Yes, sir.
Yeah.
And so the distribution of randomized estimator will always be given to us.
Yeah, if randomized estimator is, you see, randomized estimator is determined only by its distribution, right? If you are
So-
not given, if corresponding to every randomized estimator, there is a distribution, right? Which tells you how to do the randomization. For example, problem number 10, actually, if you look at, I think I have corrected the typo over there. Problem number 10. So your sample is from, let us look at x1, x2, xn, or IID. So let us do this so that you can have a better. Which one you want me to do? 9th I have already done. Let me see you do the 10th one so that you can understand. IID exponential theta 1. Right? Theta is given to be positive. Theta belonging to R. So exponential, yeah. This is theta. Okay. For estimating theta under a loss function, so I don't talk anything about the loss function. So there is a loss function. Consider the randomized estimator delta x. Earlier there was a typo. I have corrected that. It is now uniform n minus 1 by n x bar n minus 1 to x bar n minus 1, where x bar n minus 1 is the mean of the first 10 observations. So note that a randomized estimator is given. So if randomized is given, I need to know the corresponding randomization scheme, which is uniform. So first part says find a randomized estimator based on minimal sufficient statistic. What is a minimal sufficient statistic? Do you know in this case? Exponential? Yeah? Who asked the question? What is the minimal sufficient statistic in the exponential theta 1? The density is e to the power minus x minus theta. So what is the minimal sufficient statistic in this case?
Sir, x bar.
Not x bar, minimum, right?
X.
Right. Minimal sufficient statistic. So find a randomized estimator based on minimal sufficient statistic. X1 having the same risk as delta. So let me call this as T. So I know the estimated delta naught T would be nothing but would have a density P, let us say x star T. And what would be this density? You get the original density, which is uniform, this and this. So what is that? 1 upon B minus A. So x bar n minus 1 minus n minus 1 by n x bar n. But this is only when indicator, your xn is between n minus 1 by n x bar n minus 1 less than or equal to x bar n minus 1. So that is a density. It says you integrate this with respect to conditional distribution of x given t. So what does this become? This becomes, sorry, this is x bar n minus 1. Uniform this to this, yeah. So how much is that? So this becomes actually, if you look at, if I write down, this becomes 1 upon x bar n minus 1 minus n minus 1 by n, x bar n minus 1, indicator. So this I have to do with respect to conditional distribution of x given t, right? So what I have to do is I have to find expected value of 1 upon x bar n minus 1 minus n minus 1 by x bar n is how much? N minus n, so 1 by n, right? So n upon x bar n minus 1. Indicator that n minus 1 by n x bar n minus 1 less than or equal to a less than or equal to x bar n minus 1. Given that t is equal to t, that means x1 is equal to t. This becomes expected value of 1 upon x bar n minus 1, because this is respect to conditional distribution of x given t. So that is why I'm taking this conditional distribution of x. I write down this in terms of a because I have to integrate out these x's because conditional distribution with respect to x given t. So this becomes indicator a less than or equal to x bar n minus 1 less than or equal to n upon n minus 1a, right? All right. I again try to use the ancillary Basou's theorem, so I need to get some ancillary because here x1 is given to be t. So you can make here x bar n minus x bar 1, right? X bar, sorry, this is x bar n minus 1. So I make it 1 upon x bar n minus 1 minus x1 plus t, indicator a less than or equal to x bar n minus 1 minus x1 plus t, okay. And then less than or equal to n upon n minus 1a, given that x1 is equal to t. Now I know that this is ancillary. X1 and 2. X1 is complete sufficient, so this conditional would be same as unconditional. I'll have to check whether this is correct answer or not, but I've told you the technique, right? And then this is same as without condition. So we have to solve this. Let me just check the present version because there are normally I've just posted the assignment and normally there are this which assignment number this is 5, right?
Yes, sir.
Assignment 4, assignment 5. Let me see. Which problem is this? Yeah, I've written out. Yeah, so that is okay. So uniform x bar n minus 1 minus x bar n minus 1. Yeah. So one has to just solve this integral. It may be so normally everything would boil down to integrating whatever PDF is given as a part of your randomized rule. You have to integrate that with respect to conditional distribution of x given t. And most of the time this Basou's theorem will turn out to be useful. And that is what you just need to do. Now, in this case, it will be slightly complicated to find this conditional PDF because here the distribution is gamma, you know, because 1 upon n summation xi minus x1 has a gamma distribution. So, for example, this x bar, no, this will not be gamma, right? Because this is x bar n minus 1. So, it will be much more complicated. So, this is, but one can leave it over here that your estimator is this expected value of this quantity, which does not depend on theta. Still, it is not clear, or is it clear to some extent, or should I further elaborate it on this concept?
No, sir, clear now.
Yeah, you see, idea is sometimes the, for example, in this case, I think integrating out PDF is turning out to be complicated because when you look at uniform you look at the PDF, because for uniform in this case, let me see, I can again, because you see what is given to you is delta X. Just correct me if I have noting down the correct thing from the, so this is n minus 1 by n, x bar n minus 1, x bar n, right? So what is this PDF? If you look at the PDF of uniform is nothing but 1 upon b minus a. So 1 minus n minus 1 by n, which is 1 by n, x bar n minus 1.
X bar n minus 1.
What?
Okay.
What are you saying?
So it is x bar n minus 1, the interval, the right side of the interval.
X bar n minus 1, na? Yeah. So this is same as n upon x bar. So I tried on the density including the range. What is the range? Your A should be between n minus 1 x bar n minus 1. This is what your range is, right? Is that okay? What I have to do is the estimator which has the same risk as this, let me call this as delta naught x, which will depend on t. This has a density p x star a. And what is a p x star a? That is same as expected value of p of x of a, given that t is equal to t. So let me call this as PTA, because it will finally depend on the value of the sufficiency, PTA. So T is sufficient. So that is what you have to find. So that means you have to find the expected value of this, the PDF of this randomized estimator with respect to conditional distribution of x given t. So which is same as expected value of n upon x bar n minus 1. Indicator that n minus 1 by n x bar n minus 1 is less than or equal to a, is less than or equal to x bar n minus 1. Given t is equal to t, because yes, expectation you have to take with respect to conditional of sufficiency. T is equal to t means t in this case was x1. Okay, let us try to do this. This is same as, now I have to get rid of this conditional expectation. So somehow I get an ancillary statistics over here, because it is a location one, e to power minus x minus mu. I can subtract and add the same thing. So this is same as expected value of n upon x bar n minus 1 minus x bar x1, sorry, minus x1 plus t, because x1 is given to be same as t. Indicator n minus 1 by n minus 1 by n, x bar n minus indicator of n minus 1 by n, x bar n minus 1 minus x1 plus t, less than or equal to a, less than or equal to x bar n minus 1 minus x1 plus t. This is what it becomes, and given x1 is equal to t. But now this x bar n minus x1 is ancillary, x1 is complete sufficient, so this expectation would be independent of this quantity. So expected value of n, x bar n minus 1 minus x1 plus t. Indicator that n minus 1 by n, x bar n minus 1 minus x1 plus t, less than or equal to a, less than or equal to x bar n minus x1 plus t. Now in this case, slightly this, I cannot go beyond this because finding this expectation in a closed form would be difficult. But I know that this quantity is, because this is ancillary, so this quantity will not depend on theta. It would be some quantity which will only depend on t. So in this case, one will have to adopt numerical computation to implement this estimator. But as an estimator, you can write down this is perfectly fine. Because beyond this, you cannot get the expression in a closed form. All right? Is that clear?
Yes.
Okay.
Answer in question number 7.
Question number
7.
7. Yeah. Tell me.
So here we will consider the likelihood function.
Yeah. So you see, likelihood function depends on what is being observed, right?
Yes.
Right. What is being observed here is those x's whose values are less than or equal to c, right? And for the values, for the observations for which values are greater than c, the only thing I know is that they have lived larger than c, right? So your likelihood function Lx theta in this case would become observed values are y1, y2, yn. So, and their density would be how much? E to the power exponential theta. So 1 by theta to the power m, e to the power minus summation by I by theta. For I is equal to 1. Remaining n minus 1 are not observed. The only thing I know is that they have lived larger than c. And what is the probability of a particular observation lying more than c? In the exponential case, e to the power minus c theta, right? Because I have not observed their value. So it is what I have observed is the probability of observing that is e to the power minus c theta to power n minus m. Is m is e to the power. Now you can maximize this with respect to theta. Is that clear? Because in the exponential case, probability that any observation x1 greater than c is nothing but e to the power minus what is the density I have taken? C by theta, right? Exponential 0 theta. So I am using exponential, so e to the power minus c by theta. Because for n minus m, I have not observed their values. What I have observed is that they have lived larger than c. So what is the probability larger than c for a particular one? E to the power minus c by theta. And there are n minus m, and they are acting independently. So that is why this to the power n minus m. Is that okay?
But n minus m are those which are less than c.
Their values are exactly yi's that you have observed, right? Because what is saying is x1, x2, xn is a random sample from x1. Let c be a positive constant. What is being observed? So the thing which I have observed is only those xi's whose values are greater than c. I have observed only those values which are greater than c. Yeah, so less than c I have not observed. So observed values are y. So this is not this. So what is being observed is, let me call this as. So what is being observed is only those xi's whose values are greater than c. Suppose the observed values are y1, y2, yn. So they are greater. So they are so they would be 1 by theta m e to the power minus 1 by theta summation by I is equal to 1. But for remaining one, that is, I think both the side we have. See, this is the problem. There is no proof check, and then there is actually it would be like this. What is being observed is only those xi's whose values are less than or equal to c, right? That is what it should be. So that is, and suppose the observed values are remaining n minus observation that exceed c are not observed. So what is being observed is for remaining ones that they exceed c. So that is e to the power minus c by theta to the power n minus n. So just correct this typo. In the second line, you just add. So there is a typo. The second line. What is being observed is only those xi's, third line in fact, only those xi's whose values are less than c. Third line greater than c, whose values are less than c. Only those are observed. Suppose the observed values are y1, y2, ym, and remaining n minus observation that exceeds t. So that should be. Is that okay?
Yes, sir.
Yeah. So these are probability that these are n minus m are exceeding c. This is so for them I have only observed that they have lived larger than c. That's all. So that is our likelihood. And now you can think of maximizing this. Okay. Any other doubt anybody has?
Sir, in assignment 6,
Right.
question 1, part 6. Sir.
Part 1, part 6.
Yes.
Okay, so what you have to do in each of the following cases, find the UMV of psi theta if it exists, right? So 6th part, right? Okay.
Yes, sir.
So what is the density over here? First, I need to find out what is a complete sufficiency. So it is 1/2 theta to power n. F theta x is 1/2 theta to power n, right? And then indicator. Let's take indicator that mu naught minus theta. So product I is equal to 1 to n. Indicator mu naught minus theta less than or equal to xi less than or equal to mu naught plus theta, right? Which is same as saying that 1/2 theta to power n. Product I is equal to 1 to n. Now this can be written as indicator of modulus of xi minus mu naught is less than or equal to theta. Is that okay?
Yes, sir.
So this is same as 1/2 theta to power n because I'm trying to get the minimal sufficient statistic. So I'm trying to squeeze the data as much as possible. So this is same as maximum of mod of x1 minus mu naught. Mod of x1 minus mu naught. Right? So in fact, this will turn out to be the complete and sufficient statistic. So T certainly, which is maximum of mod of x1 minus mu naught, mod of xn minus mu naught is sufficient, just follows from here. Right? Because of factorization theorem, this same as psi t theta. What is the density of T? Can anyone tell? Can you tell what is the density of T? Now note that x1 minus mu naught is uniform minus theta to theta, right? X1 minus mu naught is uniform minus theta to theta. So if I take the modulus, it will become a uniform 0 to theta because it will be still uniform 0 to theta. So it is a maximum of n uniform 0 theta. So what is that? N times t to power n minus 1 by theta to power n. And this is complete, you know that, because you can look at expected value of h of t is equal to 0 for every theta greater than 0, implies that 0 to theta ht n t to power n minus 1 theta to power n dt is 0, which implies that 0 to theta ht t to power n minus 1 dt is 0 for every theta positive. That means h theta, the derivative if you want, otherwise is 0 for every theta positive. But your t only takes value greater than 0. That means probability that, so that means h theta is 0 for every theta greater than 0. So probability that ht is equal to 0 is 1. Because t only takes positive values, right? Maximum of this, and for which h is positive. So this is also complete. Is this okay up to this point?
Yes, sir.
Okay, so t is complete sufficient. So I just need to get the UMV, I just need to get expected value of t to power r. Let's try to see what is expected value of t to power r. Expected t to power r is how much? You can see from here, n upon n plus r into theta to power r. So that means expected value of n plus r upon n t to power r is same as theta to power r. What is this? This is a function of a complete sufficient statistic whose expectation is theta to power r. So UMVU is n plus r upon n t to the power. Is that okay?
Yes, sir.
Yes, any other doubts anybody has? Oh, we have exceeded 3. So, okay, if anybody wants to ask something, may stay back. Others, if they want, they can leave. Any doubt? So tomorrow we are meeting at 8 rather than at 11. Yes, and does anyone has any doubts?
No. So post the solution.
So try to do those problems tomorrow. Again, we'll meet and try to clarify. It looks like some of you are still not very clear with this randomized estimator. I'll try to further clarify it tomorrow morning at 8 so that you can master this whole concept. The idea is very simple. That randomized estimator, there is a density. Now, if you have to get a randomized estimator based on a sufficient statistic whose risk is same as that, take the expectation of that density with respect to conditional distribution of x given t, where t is sufficient. So everything then boils down to finding that expectation. So we'll try to take up few examples which we can work out tomorrow. So if does anyone has any doubt to ask?
Hello.
Yeah.
Sir, actually my doubt like in assignment number 1. So sir, like y is a random variable which belongs to a chi-square distribution. Then in a solution given like a expected value of y ki power r equal to 2 ki power r,
Right.
gamma mu by 2 plus r upon gamma
Right.
mu by 2.
Right.
Sir, actually, I want to know, sir, how this proof comes, sir.
How this? Okay. So let us look at. So actually, if you look at X has a chi-square density, right? What is the PDF of chi-square?
PDF of chi-square.
1 by 2 to power n by 2.
Yes.
Gamma n by 2. Right?
Yes, sir.
E to power minus t by 2. T to power n by 2 minus 1.
Yes, sir.
Now, first of all, this is a PDF. So one has to assume or one has to prove that this total integral is 1, which gives me an identity that 0 to infinity e to power minus t by 2 t to power n by 2 minus 1 dt is always 1 for every n greater than 0. Sorry, not this is same as 2 to power n by 2 gamma n by 2. Is that okay? Because this is a PDF, right? So this has to integrate out to 1. Is that okay?
Yes, sir.
So take this as an identity. This holds for any n, whatever n you take, because chi-square is defined for any degrees of freedom n. So now you have to find the expected value of chi-square n r, right?
Yes, sir.
This is same as integral 0 to infinity, because chi-square range is from 0 to infinity, t to power r into density of a chi-square on n degrees of freedom, which is given over here, right? Which is 1 by 2 to power n by 2 gamma n by 2 e to power minus t by 2 t to power n by 2 minus 1 t. I take this 2 to power n by 2 gamma n by 2 outside. What does that become? 0 to infinity e to power minus t by 2, and this becomes t to power n plus 2r by 2 minus 1 dt. Is that okay?
Yes, sir.
Let us try to compare this integral with this integral. The two are same, except that in place of n, you have n plus 2r over here.
Yes.
And you know that this integral is true. The value of this integral is this for any n, as long as n is positive. So as long as n plus 2r is positive, I can get this value from here. So which is same as 2 to power, in place of n, you have n plus 2r by 2. Gamma n by 2, so in place of n, you have n plus 2r by 2. And this was anyway there. And you know that this integral would be this as long as n plus 2r is positive. Is that okay? Does that solve your problem?
Yes, sir. Yes, sir.
Okay.
Thank you.
Any other doubt anybody has?
So,
Yeah.
so you said in the class that you want to pose the solutions for assignment 5 and 6.
No, 5 and 6 I will not be able to post.
So, sir, can you please just give us the answers, like for assignment 6, we have questions like find the UMVUE. So can you just give the answers so that we can tally our
No,
answers?
I haven't worked it out. That is the problem. Otherwise, I would have posted it. But we can tomorrow, if you ask me specific ones, few of them you may be sure that you have done it correctly. If there are few doubts, I can always clarify if.
Okay.
So tomorrow, just come with your, just try to see which if you are finding difficult, whatever is there, and I can just browse through the method. Or if you tell me the estimator, I will be in a position to tell whether it is correct or not. Right?
Okay, sir.
I would
And sir,
still try to see tonight if I can give you some answers, but I'm not very sure because it involves a lot of work, and solving it in the class is always easier and much more enjoyable. And, but anyway, I'll try to do something tomorrow. Let us try to discuss it tomorrow. Or if you have any specific question which you want to discuss, we can discuss it now.
no, sir, not now. And sir, in case after the tomorrow's class we have any doubt, we can mail you, right?
Yeah, mail you can do. You see, I have a social obligation to fulfill. I'll be going, but then I'll try to answer your questions through email.
Thank you.